condition, we need to avoid the fluctuation of voltage. So we can go for the fax devices. So fax devices is applied in transmission system. Custom power device is applied in a distribution system. But the structure of the series active filter or shunt active filter or UPFC and UPQC, both are same, but only the names are different based on the applications, right? So this is the structure of the indirect current controlled shunt active power filters. Now here we have a non-linear load. So this is one of the non-linear load. So you can take the supply in MATLAB, you can take from the source, you can use that block AC source. Here we have a non-linear load. You can use for the diode rectifier. Diode rectifier is also one of the example for non-linear load. Or you can also connect after the diode rectifier, you can connect some inverter. Then inverter connected to maybe for some induction motor drives. It is applicable for electric traction application also. So in electric traction also, we need to improve our power factors, or we need to focus on the power quality. We can also use this type of devices also. So we can use some non-linear load, diode rectifier combination and LNC. And after the diode rectifier also, we can connect some inverter also. Adum pannalam. So right. So here we can, inside the block, you can use for a non-linear diode rectifier load. Again, this is one of the voltage source inverter here. It is you can use for single phase or three phase. Again, there are two factors we need to take for a feedback. One is we have to balance our capacitor voltage. We need to balance our capacitor voltage. So we need to provide the constant voltage to these inverters. So that's why we are going to use one proportional integral controller. So normally why we go for the proportional integral controller means the first point to reduce the steady state error. So next to improve the transient response. So this is the main reason we go for the proportional integral controller. For example, proportional integral controller alone, when you are going to apply the P controller alone for any system, so it is a gain value, proportional gain value. When you have a more gain, what will happen? You have a more steady state error. But at the same time, you have a good transient response, like a startup transient response. Right? When you go for the integral controller, it is a reverse one. We have a minimum steady state error, that is called ESS, steady state error. Mathematically, we are representing ESS. Then poor transient response. So whatever the drawback in a proportional controller and plus in proportional controller, similarly, whatever the drawback in I controller, integral controller and benefits, then if we combine together, then we can go for a PI controller to reduce the steady state error and also to improve the transient response. So that's why we go for the proportional integral controllers. And also one more thing, so for particular percentage of input voltage, maybe for example, our input voltage, let us take for a 230 volt supply. Then we can take only for some particular percentage, maybe plus or minus 20% or 30%, we can vary our supply voltage. Then we can regulate our capacitor voltage and also we can regulate our load voltage also. But more than 30%, what will happen? Mostly the PI controller not performed well when you go for some percentage limit, maybe a 30% or 40%. It will be performed only for some percentage. It may be a 20% or to 30%. When you go for more than 30%, it won't perform. So in that case, you can go for the better fuzzy logic controllers, sliding mode controllers, the neuro controllers, you can linear quadratic regulators. You can go for such type of controller. We can apply more than the 30% or 40% disturbance also. It will regulate our capacitor voltage as well as our load voltage. So this is the main purpose why we go for this PI controller in the shunt active filter is we need to balance this capacitor voltage. We need to provide the constant voltage even though there is a variation of the supply voltage or there is a variation in the load voltage. So you have to maintain this capacitor voltage as well as our load voltage is constant. Then some cases you need to change your reference voltage, then the controller also going to be perform well. Whatever the reference voltage you are going to change, the same voltage is attained in the voltage across the capacitors. So suppose even you are changing the input voltage and then set point, suppose the capacitor is not controlled, means your controller parameter is not properly designed. So next we can go for the another one more thing. So we can go for a sine omega t from the supply voltage. So we have to take the feedback, that is sine omega t. Then you can multiply from some constant getting from the PI controller. Then you can multiply, you will get the reference current. So that's why it is called the indirect current controller. So we are not generating our current directly. We are not giving it directly for our reference current. That reference current is derived from our outer loop, that is a PI controller. So that's why this is named as a indirect current controllers, right? Then again inside the current controller we have a hysteresis current controller and inductor average current mode controller and peak current mode controller. Different types of current controllers are there. So why we go for this current controller is, actually in this paper they are employed for the hysteresis current controller. Here what is the purpose of this current controller is, so we need to maintain a good power factors. We need to maintain the pure sine sinusoidal waveform. So that's why we are going to use for a current controllers. So now reshaping, we are going to compensating our current, source current. So now that is injected by our filter. So that is Shunt-active filter. So now based on that compensation, then we are reshaping our source current to make our non-sinusoidal current waveform into sinusoidal current waveform. So once if we have that's why we go for this current controller. So this is the controlling our source current, So there are two loops are available. One is the outer loop, another one is the inner loop. So outer loop is a PI controller. It is used to regulate this in the shunt-active. This is the structure of the shunt-active filter, like this LR, inverter and capacitor. This is the structure. In this structure, I want to regulate this capacitor voltage. Then I want to control the source current. That's why we go for this current controller, right? So that's why we go for current controller and PI controller. So this is the hysteresis current controller. In the previous block, you know very well about the PI controller transfer function. Output of PI controllers may be some K value. Sine omega t taken from the supply side. Then we can multiply generating our reference current. So in MATLAB, we are going to use for the relay one block is available. So in the relay block, the upper limit and lower limit, there are two rows are there, upper limit and lower limit. So we have to feed the band values, right? So this is this center point is indicate for the reference value. So this is the center point, reference waveform, reference current. This is derived from our outer loop. Outer loop means PI controller value multiplied to sine omega t. That is the reference current. So this is derived from the waveform derived from our outer loop. This is our measured waveform. So this is taken from our supply side, actual source side. From the source side, we are going to generate this waveform. Next, so now these two we are going to compare to generate the PWM pulses. These pulses are applied to the inverters. So through the controller, we are taken a feedback from the capacitor side, we are taken a feedback from the source side, current waveform. So through this, by using this feedback, we are taken a reference current voltage and current. Through this, we are generating the pulses. It is applied to the switches. Now we are going to regulating our capacitor voltage as well as our source current. So this is the concept to begin for the shunt-active filter. So this is the normal voltage source inverter actually. So in the previous block diagram, you have a voltage source inverter, one single block. Inside you have a single phase voltage source inverter. We need to provide the constant voltage, maybe S1, S2 going to be operate for one mode, then another mode, these two are going to be operated. Again it is connected to the line, right? So this is the single phase inverter. So we have to construct this circuit, and we can take feedback, and also we are going to design for a PI controllers. Okay. So now we will move to the MATLAB. So the inside this current controller, I already told you, this inside the current controller, whatever I said for the hysteresis current, upper band and lower band, and the reference current and measured current, this is the source current. So source current taken from the line, so reference current is derived from our controller. So this is inside you have a hysteresis relay, inside we can feed the band value, then we are generating the pulse. Pulse is applied to single phase voltage source inverter, it consists of 4 switches, right? So now we can go for a MATLAB. So again go for a Simulink library browser. Okay, so I want to construct first. So let us take, this is the one of the shunt active filter. So now we have a source here. This is for source, right? We have a source inductance and resistance. Again you have a non-linear load. I already told you can use for the diode rectifier. So for diodes we can form it as again a capacitor, and this is for automatically we have to change over the load. One particular time it will be acted as a 10 ohm, after some particular time period it will be 25 ohm. For automatic purpose they can use some switch also. So first we will connect source to some non-linear load, right? So let us take our Simulink. So I want to construct this circuit. I need a source, I need 4 diodes and a capacitor and a load, right? So first and also I need to measure the current and voltage. So you can go for the simulation. So take again go for a SimCap. So create one new model, then go for a SimPower system and specialized technology, power electronics. Then again you can take for a diode and elements, go for a series RLC branch. So next electric source, take for AC voltage source. Then I want to measure for current and voltage waveform, take for current waveform and voltage measurement block, right? So first you connect for so use this component. Okay, so I want to remove the current measurement and diode letters, then just to go for a right click, format, show block name. Then first you take for the source supply voltage, then connect for the source current. So before that you can connect some R and L value. So source resistance and RL, just source resistance and source inductance, and then you can connect some load inductance next. Then you can connect diode. So control R is rotated. Okay, so then just copy. Then you need capacitors. So capacitor. Then you can connect some. So this is one of the non-linear load. Examples for non-linear load. So this is for R value. R value, you can just connect like this. So you can connect to the So here you can connect for a voltage. Okay. So first all of you complete this structure first. So all of you complete this structure first. So whatever we are done in the morning, same thing you have to do it. Same procedure, so same pattern. You can construct, and we need to enter the value, then take power guide block, and also go for simulation and change the simulation parameters. Then afterwards you can run the simulation. Right. Now we go for the power guide block. So you can take for power guide block here and then go to the circuit. So let us take our supply voltage is 230 volt. Uh, 230. So here 2 millihenry 0.1 ohm. So here 2 millihenry. So 2 millihenry 0.1 ohm. So here 230 volt. Here we have to give for the peak value. Suppose for a 230 volt RMS voltage, then you can convert for a peak value 230 into 1.414. So multiply 1.414. Supply frequency default 60, then you can change to 50 Hz. So now supply side is 230 volt, 1.14 is we have to convert for the peak value. Then 50 Hz, actual circuit value 0.1 ohm RS, source resistance, source inductance 2 millihenry, load resistance 0.01. So this is for R only 0.01. So capacitor value 1000 microfarad 25 ohm. Capacitor value 1000 microfarad. Here you can change for 1000 microfarad. This is for 25 ohm. Then go to the again Simulink library browser, then go for zinc. In the zinc you can take for the scope. Again in scope you just go for the parameters. In the parameter you can go for a history, remove the data point, limit data point, apply. So next you can also increase the number of axes to apply. So you can measure the source current and the source voltage, and again load current, load voltage also. So you can connect the load voltage also, load side voltage. Okay, right. Now go for a simulation. In the simulation you can go for a simulation configuration parameter. Then change the solver 23 dB. Then change the stop time also 0.1. Then apply. Now you can run the simulation. So now you can see the waveform. So now this is the source current and source voltage. Now the source current is not a pure sinusoidal waveform, right? It contained for a non-sinusoidal waveform. So you have a supply, pure supply, AC, sinusoidal AC supply. It is connected to one non-linear load. Then afterwards we are going to observe the source current waveform. So from the source current waveform, just to check the source current waveform here, it is a non-sinusoidal waveform. So this is simply called as a harmonics. Right, now we need to maintain the pure sinusoidal waveform. Then we can go for the one of the FACS device called as a shunt active filter. Right, next I want to check for the total harmonic distortion. Right, how do you check for the THD value for the source current is, let us take for the scope, copy, and again you can paste, and then change for the number of axes is 1. I want to analyze the THD for source current. So you just connect the current source current waveform, then go to the scope. In the scope, go to the parameter here. In the parameter, go to the history. In the history, just save data to workface. In that save to the data workface, you have variable name. In the variable name, you just give some variable like, so now source current, let us take for IS. I want to find out the THD values for source current. So that's why I'm going to give the IS value. So wherever I want to find out the THD for any type of waveform, you can do like same pattern. So apply. So now next you just run the simulation. Okay, then go to the power guide block. In the double click the power guide block. Then go for a FFD, fast Fourier transform analysis. So FFD. In that FFD, I already saved the one variable name IS in the scope. Right, same variable is reflected in the power guide block also. Just click. Suppose I want to find out for one particular window for a THD, then select for the FFD. Select for the FFD. So what is the starting time? 0. So let us take for the starting, maybe let us take for the starting time maybe. Once the response is settled, then you can start for the starting time. Let us take for a 0.03 starting time. So now here starting time is 0.03. Take for number of cycle 1. So here fundamental frequency 50. So your switching frequency, for example, let us take for a 5 kilohertz. So now you just display. You can find out our THD value, total harmonic distortion is 83.74. As per the IEEE standard, we have to maintain for a less than 5%. Less than 5%. But here THD value is 83.74%. Right? So first all of you complete up to this, up to what I completed. Please everyone complete up to this. Values, okay. Okay. So take down the values. Supply side 230 pa. 230 into 1.414 put. Open பண்ணி பண்ணு. உங்களுக்கு வந்தது கட் ஆயிடுச்சு என்னாச்சு? ஓகே சரி சரி. கனெக்ட் பண்ண தெரியுதுல்லம்மா? ஓகே. உங்களுக்கு சார்? ஓகே. உனக்குடா என்ன பண்ணிட்டு இருக்கீங்க? ஓகே.
மேடம் பெரிய கீழே போயிடும். நம்ம பர்ஃபார்மன்ஸ்
வயரிங் பண்ணுறது தான் நம்ம இதில் பண்ணோம்ல அதே மாதிரி தான் இப்போ VLSI
அதுதான் ஓகேல்ல ஓகேவா மார்னிங் இப்படி மாற்றிட்டோமோ மார்னிங்கில் மாற்றிட்டோமோ அதனால் வரலையோ
அது ரிசீவர் இங்கே ஆகும் லைட் என்ன எரி
ஓகே இப்போ ஓகேல
பார்த்தேன் பாஸ் பண்ணி பார்த்தேன் ரெக்கார்டு
ஓகே ஓகே காலையில் பார்த்துருக்கணும்
சார் பார்த்தேன்
ஆ
ரெக்கார்ட் ஆச்சு
அப்போ
அதுக்கப்புறம் ஆகலை டெஸ்ட் பண்ணிட்டு தான் வந்தேன்
ஓகே ஓகே 1000 மைக்ரோஃபரட் மேலே இருப்பாருப்பா அங்கே 1000 மைக்ரோஃபரடு 25 ஓம்ஸ் ஆறு லோட் ரெசிஸ்டன்ஸ் RL 0.01 ஏமா பண்ணலையா ஆ ஓகே குட் பண்ணிட்டியா ஆ வேல்யூஸ் அது இருக்குப்பா 2 மில்லியன் 2 e பவர் -3 போட்டுக்குப்பா 0.1 சோர்ஸ் போட்டுக்கோ அதிலே போட்டுக்கோ சப்ளை வோல்டேஜ் 230 இன்ட்டு 1.2 414 போட்டுக்கோ அதுதான் 50 ஹெர்ட்ஸ் மாற்றுக்கோ
சார் இந்த பேப்பர்ல இருந்தா நீங்க எடுத்தீங்க
ஆமாம் பேப்பர் தான்
உங்களுக்கு இப்பதான் நான் நிறைய விவசாயிக்கே
ஓகே
Sir, MATLAB circuit, sir.
சார்
எடு எடு எடு
போடுறேன் சார்
வருதாம்மா எடுத்துட்டியா பண்ணி பார்த்துட்டியா டிஹெச்டி பார்த்துட்டியா எவ்வளோ வருது டிஹெச்டி சார் ஓகே அது ப்ராப்ளம் டிஹெச்டி பார் மெயின் அதான் டிஹெச்டி சோர்ஸ் கரண்ட் பார்